So good morning, everyone. So I hope that you guys can see the slides by now. And in slide, we include the QR code to our report and to the website as well. And so you can scan it um, to see what the content in there. And so we will go straight into the content. So we are the Sortan team, which is a Khmer music recognition project. And for the Sortan team, we consist of me, Bunsy Chhay, and Mr. Sovichea Sinath. For our supervisor is Miss Emrudi Supan Nguyen, and the co-supervisor is Mr. Bun Liep. So for the content of today, we will be talking about the problem statement of an objective, and we also include the scope and the limitation as well. We will talk about literature review, Sortan framework, implementation, testing, test result analysis, and then we will do the demo of our application, and then finally is the future work that we propose for the problem statement. So as you know, like for competitive pop music practitioner, filmmaker, and so on, will have the exact moment that they hear a Khmer music in the public place and or elsewhere, but they don't know what that song is. Therefore, they will become curious about it because like that song is leads or like attract their mind. However, most of the time, it is hard for them to find those music without having any knowledge about it at all by guessing over and over again or by asking the nearby people, because in some occasions they will be shy to ask one. So our objective is to develop an Android application for Khmer music recognition called Sortan. And for the scope and the limitation, we will make it to recognize all Khmer music that exists in our database, to implement a music recognition algorithm that is accessible for only our application by now through the use of the API. And last one is to apply a simple and workable encoding process that can generate fingerprint and use it in our system. Okay, for the literature review, we have during our research of the project, we have looked into many fields like neural network, image processing, and spectral analysis. And at the end, we come to the conclusion that only we will use the spectral analysis to implement in our project, because it is more reliable and it is easy to implement one using that field. For the Sortan framework, so for the Sortan architecture, the user will start by recording the audio when they open their the application on their Android phone. When they do the search, after a short period of time, the audio will be sent to the server, and then the server will use that wave audio file to search for the fingerprint in our database. After the mic is found, the server will get the song info and link from the database, and then return those info to the smartphone back, and then display to the user. For the front end design, we will have the loading screen, or what people call the splash screen, which is to show the Sortan brand logo to the user for 3 seconds, and then it will automatically transition to the main screen, which is the search screen. In the search screen, it will include the search button in the middle of the screen, which is to provide the search functionality to the user. The animation and the countdown timer will be displayed to indicate that the app is listening to the background, and the result button uh, on the right hand side and up there is to give access to the previous result, so that the user can look back. For the result screen is to show the song the detail to the user. The detail include the song title, the song thumbnail that we get from the YouTube, the singer, and the other action part, which include the URL to the YouTube, and the other button that allow the user to go back to the search screen. For the result, but not just search, is to show that show the user that they haven't searched any song yet, so they may click on the back button in order to go to the search screen. For this one is the error screen, which is just to show the user that the application received the error response from the server. And for the history screen is to show the user or their previously search new music. However, the screen is just in the future work of big, and right now there is no implementation of functionality in this screen yet. For the Sortan framework, for this one, Sortan application is built using the Flutter framework, and it utilizes some packages like Flutter Sound, which provide the functionality to record the audio permission handler, which allow the app to get the permission from the user. Basically, here Sortan will ask permission for the microphone and the low-cost storage. Provider is the package that allow for state management. Dio is the package that allow to use the HTTP request that we will be used to send the file to the server. Connectivity is the one that allow the app to check for the internet connection, but the currently there is the internet connection on Wi-Fi or on cellular. And the last one is the URL launcher, which allow the app to launch the video in the YouTube.
Okay, so we going a bit fast. If somewhere not clear, everyone can check our report. So for the backend side, the backend framework, we use Python as our primary language, and for our database, we use a SQL-like database called PostgreSQL, and we also use a handful of libraries such as SciPy for generating the spectrogram, which everyone will see soon. Pandas for connecting with NumPy and do a lot of computation for us when we performing the search. Flask is our web framework so that our front end or our mobile can connect to it. And of course, PyDub, which is a library that to load the audio. First, we need to collect data. So we have a library for that, which called YouTube which can download our music and turn it into a WAV file. And YouTube can only download from all the source of video, but we choose YouTube because it is freely accessible to everyone. Implementation. So for our performance process, an overview is like Mr. Bunsy have described. The user will be recording the audio, send it to the server, get the result from it, and show the result. For the recorded part, first the application will ask for internet connection. If there is not, it will just show there is no internet connection. If there is, it will start to record when the user presses the record button. And for a certain time period, it will stop. It will form a WAV file. Again, it will ask for is there internet again. In case there is not, if there is, it will send the WAV file as a post request to search for the song that they are looking for. For sending the audio server is straightforward. It's just initializing the API, preparing our file in a multi-platform data, and then send a post request that you mentioned. For the response came back, if there is an error, there will it will show no result. But if there is not, it will show the result like our screen that we show before. Okay, so for the data collection process, it's a bit manually. First, we go to YouTube. We add any song that we want to test, we want to try into a playlist. Then we use YouTube to download those into a collection of WAV file. And then we downsample it, change the sample rate to 44.1 thousand hertz, and change the audio tone from stereo from two channel to monotone, which is one signal, one channel. After that, we will send everything to the server where we'll pre-process the music data over there. So first, before we do anything, we have to validate if our file is valid or not. So first, check is there a file that we send it? Is it a WAV file? And then we check is the sample is correct. And lastly, we check if it's monotone or not. This is just a precaution in case that we done a lot of sending music to a server and that it does not have the metadata that we agree on, and everything will be not usable. Next step is generating a spectrogram. So spectrogram, so an audio file is a continuous form data. It's just one large data. So what we cannot get much information from it. So instead, we use spectrogram, which a visualization of the audio, and it will give more information about that audio file than just a plain raw WAV data. So first, we use the WAV data. We put it into a function called spectrogram from SciPy, and we use a Hamming window, a window function with the size of 4096. Then we can get the spectrogram. So this is a spectrogram. On the x-axis, the vertical axis, is our frequency, and our frequency is half of the sample rate, which is 22.05 thousand hertz in this case. And the vertical axis is the frequency, and the horizontal axis, which is the bottom, over here. This is our time, and it's in second, or yeah, it is in second. So this is not just the special part that spectrogram gives. Spectrogram gives three things: the vertical axis, which is frequency; horizontal, which is time; and the color over here is the amplitude. The color in the middle is amplitude, and that is the same exact time and exact frequency. One more interesting information that spectrogram will give us back is it's chopping that one large continuous sound data into multiple smaller discrete format data. So each of the cell here, each of the square here is roughly around 10.76 hertz and 0.092 second. And from this, we can do a lot of things, such as filtering and analyzing on each of that 0.092 second from 0 to the end of the song time. So this is what we this is from the this is a zoom in spectrogram that we showed before, but it's zoom in real close, and as you can see, the entry we can see the the range of, we call it the bin frequency change from the color. It's from dark green to light green to dark green and back to light green. Like you mentioned, that each of that cell is roughly 10.76 hertz and 1 second or 0.92 second. So how do we get this number? We get it from our metadata, which is the sample rate and the window size. And that 10.26 hertz, 26 hertz is just sample rate divided by the window size, and the time bin, which is that 0.092, is the other way around, which is the window size divided by the sample rate. So now we have a discrete level data, discrete data on each of 0.092 second. So for each of that 0.092 second, we're going to pick 6 loudness frequency on 6 different play. We do this because in theory, it will pick up different instrument, different voice, different sounds that live in different frequency range, because a guitar, a drum, and our voice are those at different frequency rate. So rather than take everything, we just filter out 6 parts of each 0.092 second. So I hope everyone can see this, but this red dot here is what the point that we pick, about that 6 point that we pick for each time frame for that 0.092 second. Let's zoom in a little bit. And here we can see that the red dot are following the pattern, some like a pattern, the yellow part and the red dot here. So it's kind of trying to search pattern across the time, each pattern, one pattern at a time. Okay, so let's talk about what we can store into the database that make it searchable. So we have frequency and we have time. Frequency always a fixed value data. It's always 0 to 22.09, 09,000 hertz. But just to make it more simplified, we're not storing the actual frequency itself. We're storing the index of the frequency bin, because sometimes when we, most of the time when we record it on 2 different devices, it produces slightly different frequency range. It's so 14.5 frequency and 16.00 frequency. It's almost the exact same. So we just normalize it and put it in just and say it's just the same, because what we recorded from our phone and what we got from our source will always have this slight different change of frequency. Okay, so frequency we can just store it. How about time? Time is a bit harder because time is not fixed. It's always dynamic. It's either 3-minute song or 10-minute song if that's possible. And our recording is always 10 seconds. So we cannot just save the time and then perform an SQL query for that exact same time. It would not work. So rather than storing a time as a unit related to the time axis, we can store time that related to one another, to another point. So a simple analogy is that if I and my partner, Mr. Bunsy, want to know where each other live, but we don't know the exact location, we will pick a random place that we know. For example, I was university, and I will tell Mr. Bunsy that I live 5 blocks from the university. We use that same analogy to apply into this method here. So rather than storing the random point here, the white point here, as exactly as 3.5, 3 minutes and 5 seconds, we store it. Say if we store the time as it is 5 seconds, it is a 2 second difference from this red point here, and this red point. Let's make it a bit simple to say. We call it an anchor point. So we got something like this. So this, the red point, the white point, and their time difference. So we store 2 frequency and 1 time difference. It's a fingerprint. That is what we are calling a fingerprint. A fingerprint as human is something small that represent something big. Like when you accessing your phone, you only scan your thumb or your finger to access your phone. You don't need to do a full body scan. So it's the same thing here. We choose these two frequency and one time difference to representing two different entire time frame and frequency. So we eliminated thousands of data just to pick two frequency and one time to represent it. And just to make it faster to search from time to time, we can, one anchor point can have many other frequency points. Because doing this will create some like a unique pattern to search. If we just storing one anchor point and one point pair, it would produce a lot of data for our database and also a lot of similar data in our database. So we try to limit it a bit. We can choose multiple points for that anchor point to relate to that anchor point. That way, it generates a more concise, a more uniqueness, but it's not unique. Just not as a lot of the same data. It's those similar data, but not exactly the same all the time. Okay, so so now we get our anchor point frequency, and the time difference. We can't just store everything as different part of the table in our SQL database, but doing so will cause trouble when we search because there's three different parts. When we search, we use a where and or and and. Where anchor point equal this, and point frequency equal this, time difference equal this, or and blah 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 a lot. It will produce a complicated search and also store a bit more byte, in this case 12 byte. So rather than that, we simplify it a bit by composing those data points into one single ID, which we call lookup ID, and it's just separated by number 0 in between each point here. So we do this. We can just create a temporary table and join it later on, and also it only costs us 8 bytes for each record. Okay, let's go to so for that process is the searching. So first, we verify the file. Like we mentioned, we generated the fingerprint, the process that I just show, I just present. And SQL query search the lookup ID using SQL. Now group those fingerprint or pattern or target zone, those group or point. We also call it target zone. We group them together and then group those target zone into by music ID. And then we can eliminate any music that did not produce 10 seconds or 5 seconds or any second that the clip will be sent to. If it does not exceed or equal to those seconds, we just eliminate it. It's not the song that we are looking for. Okay, so this is might be a bit confusing, but let's go with it. On the left-hand side, I have the clip that this color point are representing different anchor point, and we eliminated the target zone just to make it easier to view. And this on the right-hand side is the music number 1. So now we got a lot of music. So we need to find the correct one by calculating the time different max section. It's just a harder way to say we want to find the exact same sequence of music that's going to play. So these two look fairly similar. It's just that the music one is a bit more leaning to the right. It can say that the song start at 5 seconds, but I record it at 5.3 seconds. So it's a bit shifted. So we try to find the correct order of the song to match the result. So in this and music number 2, the frequency are all the same. The red still the same. The blue still the same, but it's just not orderly aligned on the time axis. So what we do, we calculate the mode of the time difference. of each song, and then we pick the one that with the most consistent part. The mode is just a number that appear the most in a set of number. So let's compare the clip now, the recorded clip and the music. As you can see, the distance are fairly similar, almost the same: red, yellow, blue, and green. So this is my likely be the correct audio. And for the clip to music number 2, it's not very consistent. The red and yellow are the same, but the blue and green are very, very different. And for the clip number 3, same as music number 2, it's not very consistent in the time difference here. So from all of this music, we can say that music number 1 are the most correct, the most likely music that we are looking for. Okay, so it's for testing. My partner will cover this and also the demo part. Mr. Bunsy, please come up on stage.
So for the testing, we divide in we did the search by dividing into 3 different samples of 100 search each. So it means that we did the search of 100 clips of 5 seconds in the low to mid noise case, 100 clips of 10 seconds in the no noise case, and 100 clips of 10 seconds in the low to mid noise case. And moreover, we also test with the cover and remix version of the original music as well. So with this we come to the result that we found that we managed to get the 89% of success, and only 11% fail in the 5 second one. For the 10 second of no noise, we get a success of 98% and 32%. 10% low to mid noise environment is we get 15% fail. However, the success rate is still high. With the cover and remix version of the original music, the might happen in only one condition, and that condition is that the cover and remix version need to have that one instrument that appear in the original music. And for the fail percentage, it depends on how on the song as well, because some songs start out with no without any sound at all, and some have the sound like it's so unclear. And so this is the end of the test result analysis. And so let's get into the demo part. So I will be presenting you the screen. So before going to the demo, I would like to show you our website where you can download the application, and we only available in the Android device. So when you I will send you this link, and with this link, you will be get into the home page, and on here you can see the download tab, and when you click on here, you can click the word here to download. And in some Android devices, they will have the security method like security protection. However, if you want to use our application, you can follow this step. We don't put any virus or something like that in our application, and this is the list of the song that exists in our database, and you can open this one and search with it. I will share you another screen, which is the YouTube. Wait, this. So here is the playlist, and I will show you the. I hope you guys can see my camera. Can you see me? And this is the.
I can see you.
And this is the app. Wait. Sorry for this one. For this. Change background. Okay. And so here I will play this music and I will record and do the search. And this song is called Six by Sinath. Here is the result. Here is the result of the song, and you can see this title have here the thumbnail. This one you can click on the YouTube icon to go into the YouTube application, and then you can listen there. Here. And that's all for our demo, and thank you. However, we will have one last session to talk about, which is about our future work.
Yes, Bong, and also can since we're also running a bit out of time, can you also quickly summarize that point? Thank you.
So for our future work, we will expand the data in our database, because right now we have only 50 songs, so we can only do the search on 50 songs. The next one is we will use a better hardware for our server, since currently we have our server is only 2 GB of RAM and one core of CPU. We will generate fingerprint on the mobile device directly without sending the whole wave file into to the server. We will implement on the history screen. Moreover, it is good to have the caching mechanism for the search, because it will improve our improve much about the performance of the search. And lastly, is to use a different type of the database, because right now, since the time used for searching is low. However, it is best to use like other type of database, like the time series database, because it helps to reduce much more time in searching. And that's all for our presentation.
Okay.
Thank you.
Yes, thank you very much, Bong, for for your presentation and also a very cool demo. Actually, we were supposed to have a Q&A for your session as well, but I think yes, since this application is very interesting, and if you guys have any question on how the idea came through, you can directly contact Mr. Bunsy and Bong Sovichea to he will share with you on that as well. So yeah, with that said, thank you very much for your presentation, Bong.
Yes, thank you, everyone.